Good evening, everybody. On behalf of the Department of Computer Science, Chevalier T. Thomas Elizabeth College for Women, I extend a warm welcome to all of you to this webinar on recent trends in networking. While the internet has been literally the backbone of every revolution in the past, it has gained the front seat during this pandemic. Now, the whole world is online. Given this scenario, we thought it would be appropriate to have someone who has immense experience in this domain. Our resource person, Mr. Jay Karthik, has over 15 years of experience with the network giant CISCO. Incidentally, the platform we are using for this webinar, WebEx, also belongs to CISCO. Mr. Jay Karthik completed his Masters in Computer Science from University of Madras in 1987 and began his career as a developer in routing protocols and border gateway protocol in Tata Elxsi, Bangalore. He then went on to join Cisco in US and is currently selling technology to major ISP providers, that is internet service providers like AT&T Labs US. His expertise includes routing protocols like multi-protocol label switching, etc. It is a great pleasure to have you with us, sir. The speaker has extensive knowledge and hands-on experience in networking and telecom industry. And today's presentation would be an overview of the core network, that is the internet backbone. The presentation will also cover trends and innovations in the core of the internet. The speaker assumes the audience is aware of the OSI layer and internet protocol of the network layer. Thank you, sir. We look forward for this session. We would also like you to give some insights on the current pressure or the current scenario under which network professionals are working. Thank you, sir.
Thanks once again for that excellent introduction. And I was just saying that some of you may be familiar with me or have seen my face because I did stop by the college at least once previously. Before we get started, I want to give a few shout out to some of the folks instrumental in getting me here. I want to first thank the college as well as the management. I want to particularly after our Meenakshi, who is the principal in charge, as well as Mrs. Mary Catherine, of course, with whom I've been working. She is the head of Department of Computer Science at the college. That said, folks, as ma'am mentioned during the introduction, this is going to assume some kind of beginner's level knowledge when you look at the OSI model of the network. And as ma'am during the introduction pointed out, my focus is going to be on the network layer. And with the network layer, it's not going to be focusing on the edge or the access part of the network. But when you think of a large backbone in the internet, how does routing happen there? Because whatever happens in the core of the network is what is keeping the internet afloat. In fact, even this very connection, right, between me and to some of you folks in Chennai is happening through our internet backbone. So we will spend some time focus on that particular technology that makes all of the routing possible. As we go along, I will share with you all what a route protocols is, what are some of the customers' pain points, because as ma'am was teeing this up for us, ma'am wanted me to touch on one or two challenges that service providers and just anybody, a network administrator, is particularly facing during this pandemic because there are lots of folks working from home. So the network is running hotter than it has ever been before. But somehow, knock on wood and keep our fingers crossed, the network is holding stable. There are parts of the network where there is congestion in traffic and more capacity needs to be augmented, but that's something that we can easily manage. Now, I'm going to share my slide here. I want somebody to put on the chat panel. The very fact that you can actually see my screen would help me. So when the screen pops up, somebody kindly give me a thumbs up or let me know. Awesome. Excellent. I'm seeing some messages that, in fact, the slide is visible. I'm going to look at the participant panel here to mute some lines that are making noise. And I will also hand the host key to somebody here. Ma'am, who should I hand the host key to? Okay. Okay. All right, I'm passing this to Ms. Hemavati here. So, Ms. Hemavati C is going to be the host for us, folks. Ma'am will monitor who's making any kind of audio static noise, and she may be able to mute them as well as field the questions and relay them to me. So, ma'am, you should have the key, the host key, and that's it, folks. I'm going to go ahead and start sharing again. Sorry for the technical glitch here. All right. You should be able to see this. I'm going to be in this mode so I can better see all. If you want me to go into presentation mode, I'm happy to do that as well. All right. Let's get started. Here is the gist of the agenda, folks. I want to first set the table here by talking about the network architecture to show you all where exactly my discussion would pertain to. We are going to talk about routing protocols. These are protocols that ma'am mentioned during the introduction, but I want to get a little deeper so that you'll all have a fundamental understanding of what we are talking about here. Core of the internet works with something called traffic engineering. I want to spend a few minutes explaining to you all how traffic engineering is achieved, and even prior to that, what is traffic engineering is something I would like to share with you all. There is this notion of software-defined networks. Everything is software these days, and so when you look at what is software-defined network under the hood, there are a few things large service providers such as Reliance Jio, AT&T, Verizon, folks like this are up to. So we will talk about that. They have something called SDN controllers. They have this notion of separating the control plane and the data plane on a router. What is it? Why is it? We will touch on that. But also these days, customers want to remain profitable because they are bleeding a lot of money by adding more capacity to the network, but they are not able to monetize the bandwidth they are adding because customers like us are using the network even more these days. More and more people are joining WebEx, more and more people are downloading games, watching videos. So the load on the network is increasing, but the customers, I'm calling them customers because I work for Cisco Systems and I look at large service providers as my customers. But really, when you look at these large service providers, they're not able to monetize and make more money as the network usage is going up. So they are needing to find a cost-effective way to keep their capital expense and the operational expense down. Only then can they remain profitable. So we will talk about what they're doing in this space. They're trying to separate the hardware and software and calling it disaggregation. And then there is also this notion of NFV. If you can see my cursor move here, network functions virtualization. So instead of having an expensive router, sometimes it just makes sense to take the software piece from the router and run it on a personal computer, which is very cheap these days. A powerful server is much cheaper than a router. So you, in essence, you can run the software of the router on a server or a PC for functions like route reflector, where a route reflector, if some of you are already familiar with this, would recall that it's not really taking much traffic and sending it out. It's not really routing. It is just sending the routes and information about these routes. And that can be done from a computer, strong compute. It doesn't need any forwarding capabilities to be able to route. So I want to focus on why we need to be doing what is called network functions virtualization, and I will certainly pause for at least 10 minutes of question and answer. Feel free to interrupt me during the presentation. I only have about 10 slides, so as I'm projecting my slides, if there is any question, do not hesitate to ping me or interrupt me, and if I do not get interrupted, I will make sure we have time in the end. That said, folks, let's begin here. Now, I was a student some several years ago, and when I was a student, of course, we had this book, The Computer Networks by Tannenbaum. It was part of the master's program I did, and it was one of the prescribed books. And I've read a few books, Richard Stevens' Unix Network Programming, as well as the TCP/IP Illustrated. So these were all great foundation, right? Like they definitely set me up for success when I set foot into the industry, because my first project was working on Border Gateway Protocol, BGP, as Ma'am Mary Catherine alluded to. So I took this foundational knowledge that we all learn from our college, and some of this knowledge in the textbooks are even to this day very, very important because they first give you the notion of what are the seven layers of the Open Standards Interconnect Forum that basically talks about what are these layers and what's really happening at each of these layers. These are all explained in the textbook, and some of you would have either finished computer networks as part of the curriculum, in which case you're able to associate with what I'm saying, and some others may not have been exposed to networks quite yet, but please bear in mind that it's going to be part of your syllabus. So, uh, given that this is the OSI layer, my focus today is going to be on the network layer. And as some of you may recall, TCP is in transport layer, TCP or UDP falls in the transport layer, and IP is the default protocol in the network layer. So today, my presentation is going to be focused on how to manage networks, how to manage all of these IP addresses and stuff like that. So we are going to focus on this network. Within this network layer, of course, there are parts of the network where this third layer comes into play big time, but I want to focus my attention on this service provider network. This is a very simplified, high-level network architecture. If you are a large service provider, such as Vodafone, BT, as in British Telecom, or DT as in Deutsche Telekom, NTT in Japan. There are so many key players here, and I'm looking at this from the perspective of some of the U.S. service providers because that's where I'm working as well as I'm selling to these folks. So if I think of AT&T or Verizon, I look at them as the large service provider that form the backbone of the computer. We call this the P network or the provider network. What happens here largely dictates how good a customer in the edge of the network is going to have in terms of good user experience. So looking at this network, there may be several customers. There could be colleges, campuses, towns, neighborhoods hanging off of what we call as customer edge router here, the CE router. Now the connection could be through cable, through some kind of a Wi-Fi Max, does not matter, DSL. There are so many technologies in place where people living at the edges of the network would get internet access. If you're on a cell phone, maybe you're just directly talking radio signals to a cell tower, which is in turn converting this through the RAN network or radio access network back to one of these routers here. We may call portions of this network as front haul and back haul, but I don't want to complicate this. If I want to keep this network very simple, just imagine that there are customers. There could even be businesses. If I were to look at a prominent bank in India, ICICI Bank, say they are VPN1, Virtual Private Network 1, and there could be another group, a big company in India, when I look at it, maybe there is a Tata company, and let's call them VPN2. So both of them may in turn use the same internet infrastructure here, but we want to make sure that ICICI customers do not access Tata Group customers here, and vice versa. The Tata Group here shouldn't be able to access ICICI. So even though we have a common shared paradigm here, we want to make sure that the routes and traffic gets filtered at this provider end such that one customer does not see the other customer's traffic. We have something called VPN, Virtual Private Network, that's made possible at this provider edge. Like we have several provider edge routers throughout the internet, but all of these nodes need to be connected. How are they connected? We have this huge routers. In this particular part of the network, when you think of the core of the internet, we are not talking in terms of kilobits or kilobytes. We are not even talking megabits and megabytes. 1,000 megabytes make a gigabyte, and we are still not talking gigabytes. 1,000 gigabits and 1,024 to be precise makes terabits. So we just begin our conversation at terabytes. So there is a lot of capacity needed here because imagine millions and millions of users, their Netflix video, everything gets traversed here. I want to pause for a second. If somebody has a question, feel free to put a question on the chat panel or feel free to unmute yourself and ask me any questions you may have, because I want to make sure that I set the right kind of foundation as we start. I'm getting some message that the presentation pace is good and the slides are all clearly visible. Awesome. So just have this network architecture in your mind, and please note that I'm going to be focusing predominantly on the core of the network here. One more slide to perhaps set us up. Like I said, when you look at how end users like you and I connect with the internet, another slide that kind of reinforces what I just said. We could all be hanging off of, I'm trying to see where my cursor is. I think I lost my cursor. Okay, I got it here. So if you look at us getting some kind of a connectivity through whatever is the access technology available, think of several access points, like literally, like we're talking millions of these kind of nodes here. They get connected to what is called access. And these access routers propagate the traffic through what we call as aggregation network. This is the metro or metropolitan network where traffic gets streamlined and gets passed to perhaps an edge of a network. And when it comes to a customer edge, which is probably sitting here, that would have peering or routing adjacencies with provider edge, which is the PE router. And the PE routers are all sitting at the edge and they get connected through the core. There are no routers shown here, but here is where I play. And of course, when a customer wants to access the internet, when the traffic or the request from end users like us, let us say I'm downloading a movie, that particular movie request gets fed to these routers in between. And finally, when it reaches the core, it reaches what is called the peering point, and then it goes to wherever the content is. There are multiple ways to show the network, but I'm just still setting the stage for y'all so that when I talk about more advanced concepts of what is the challenge a service provider faces, you know what architecture I have in mind. Yeah, there is a question on the chat panel. In a simulation tool, how many maximum nodes can be injected? Is there any limitation here? That's a good question. So one thing is, we are still talking IP. As you all know, IP addresses have the notion of 4 octets, A.B.C.D. And the number of nodes, the number of edges, the number of endpoints we can have are all in some ways dictated by the number of IP addresses we have. And that's one reason why IPv4, the 4-octet address, is going to be IPv6, which is going to be a lot longer IP address scheme so that more and more users can connect. That's not going to muddy the water or make it complicated for us from the perspective of the question that was just raised. How many nodes can we have? Literally, we can have hundreds and hundreds of routers here. What really matters is, do we have enough of pipes? I call them pipes so that you can envision. Like, let us say there's a pipe between Mumbai and Chennai here. I'm just looking at the west coast here and the east coast here. If this was the continental India or the subcontinent of India, when you look at Mumbai here and when you look at Chennai here, do we have enough of a bandwidth pipe here? Obviously, they may not be direct link. Sometimes there could be like intermediate hops going through Bangalore or Hyderabad. Does not matter. We need to make sure that there is enough bandwidth. If there are more users on the edge and they're watching more videos, playing more games, downloading more textbooks, and more traffic gets put on the network, we just need to make sure that we add enough of a pipe here. And you will see some of the following slides talk more about what exactly goes on in the core. Here is a topographical view of one of the customers that I'm selling to. I've just modified some of the town names so that I'm not using any privileged information, but this should give you an idea of how is the core of the network within the continental US. When I look at the US, there are several sites here. There are about 25, plus or minus few, but there are about 25 of these dots. And each one is a router, and sometimes each one of these could be 2 routers. But the idea here is that you cannot get a router in Miami talking to everybody directly. There is no direct adjacency. Miami router here in the bottom right of my screen talks to only 3 routers, Atlanta, New Orleans, and Houston. But nonetheless, Miami may need to send traffic to LA here, San Jose here, or Boston, which is where I live. So it needs to find a seamless way to get there. And there are a number of paths to get to Boston. From Miami, traffic coming from the edges hanging off of this router may have to go through Atlanta. But if this link is congested, traffic needs to be routed through Houston. or maybe through New Orleans. All of that is being made possible through the routing protocols. Now, when I recall my days at college, Tannenbaum talks about the various types of network, the various types of media, the various types of layers. Tannenbaum also talks about the notion of TCP/IP. So it does touch about IP, but it really scratches the surface. It doesn't get into what are the routing protocols that make internet work. If I think of this router Miami as an example, it is actually talking to Atlanta, New Orleans, and Houston because they are directly connected through what is called IGP, Interior Gateway Protocol. Because this whole network is managed by one administrator, this is probably going to have one autonomous system. Because even though you see a lot of dots here, who's managing it? It's somebody like AT&T, or if somebody else is playing in the US space here, it could be Verizon. But if you overlay this on the Indian subcontinent, maybe you have players like BSNL, or it used to be BSNL many, many years ago, or it could be Reliance Geo. Doesn't matter. Let's just replace whatever cities you see here with some of the prominent cities in India, and you would start asking yourself, who's managing this? It's Reliance Geo. So how is Reliance Geo making sure that all of these routers talk to each other? So because you're talking about something that is happening within the autonomous system, an autonomous system, by the way, is a set of networks managed by one particular administrator, and they have a unique number called autonomous system number. That's how routing happens. So when we talk about an autonomous system, say for India, all of India, then the question becomes the routers talk to each other within the autonomous using protocols called IGP, Interior Gateway Protocol. Now, what is an example of an Interior Gateway Protocol? RIP could be a good example. ISIS, not BGP. BGP can be used both internally and externally, but oftentimes it's external protocol. It's EGP as an Exterior Gateway Protocol. So I'll come to Exterior Gateway Protocol in a second, but still focusing on Interior Gateway Protocol, two very predominantly used protocols are ISIS and OSPF. ISIS is intermediate system to intermediate system. OSPF is open shortest path first. Basically uses the concept of Dijkstra's algorithm. If some of you have had operation research in your paper, you might talk about Taha's book where how does one salesman go from one particular place to another place and stuff like that. When you think of SPF, shortest path first, Dijkstra, the person who created this algorithm, called it SPF. And then SPF became the foundation for this protocol called OSPF. So there are two protocols. ISIS, do you want Pepsi? Do you want Coke? It's a matter of what you prefer. What is your choice? So same way a network administrator can use ISIS or OSPF to talk within the autonomous system. And when you talk from here to, let us say, Australia, New Zealand, and Europe, and somewhere else, then you begin to see the necessity for each of these routers to talk to another router in Europe to learn routers about, or rather routes about Europe. And for that, we use an exterior protocol called BGP, that is Border Gateway Protocol. BGP is the most popular protocol in the world because it can highly scale, it's robust, and there was a question around the number of routes that some of these routers can hold. We are literally talking about millions and millions of routes that a router can hold in terms of BGP routing. So here is hopefully enough of setting the table for you all to understand what a typical topology would look like. I'm doing a quick time check. We have more than, or at least 30 minutes left. Let me cruise through here, folks. Once again, when you think of what is a routing protocol, you get into the notion of interior gateway protocol and exterior gateway protocol. If you don't take anything else, walk away, please, with the fact that BGP is one of the predominantly used exterior gateway protocol, and we have EIGRP, OSPF, IGRP, and RFP. All of these are interior gateway protocols, but I focus my attention oftentimes on OSPF or another protocol that's not listed here called ISIS. So those are the two protocols that I use extensively. You get to read about this as you actually start playing on the router. I've had some hands-on experience on the router, so I know how to configure these protocols and stuff. For somebody who's just hearing the term routing protocol, just just like computer programming languages, right? These are all like languages we use to kind of like write programs so machines can talk to machines. So here, routing protocols is the language that one router would talk to another router. Like just like you have Hindi, Tamil, and English, here we have routing protocol. That's the simplest way of putting it. Now, because ma'am mentioned the pressure and challenges like being faced by the large service providers, I want to take this question from a broader umbrella. Even before we talk about COVID-19 as a pandemic, what is causing in terms of pain for a customer? Somebody might ask me, Jay, when you're talking about cutting edge innovation happening in the network in the SDN space, right? Because I mentioned NFV, hardware and software getting disaggregated. These are all some of the new innovations happening in the network. And one might ask, why should we do it? Internet is working. It works today. It worked yesterday. A few years ago, internet was fine. So why are we trying to fix something that is not broken? Well, the internet and the common backbone, it is not broken, but it is not able to handle the traffic growth. In fact, going back to my reference topology here, what I'm noticing is that there are several links that never used to be running at 80 or 90% of the utilization. Let us say there is 10 terabits of bandwidth available between Atlanta and this particular node. We'll call it Columbus here, Columbus, Ohio. So this particular node, if it has 100 terabytes, it would probably be riding at 30 or 40 terabytes, and there was a lot of headroom or bandwidth available in this particular link. Sometimes it will go up when in the customer share, and when the customer share use more network, it might go up from 30 to 40. When these links go down, let's say Atlanta Nashville link goes down because there is a failure, somebody erroneously cuts the fiber, or there is an earthquake here, or a railway track accident, pertaining to trains perhaps, because a lot of these fibers are laid along the train tracks. If there is a train accident, the fiber could get cut. So when a situation like that happens, traffic going between these two select pairs, if you can see my cursor move, might have to be routed through here. So the usage may go from 30 or 40% to 50 or 60%, maybe 70%. But with a lot of people working from home and having more and more WebEx calls and Zoom calls, this network here is really running hot. It's at 80 or 90, and some of my customers are beginning to buy more and more line cards to beef up the capacity here so they can augment what is already here. So you see, that's happening. And if that is happening, that tells me that service providers like AT&T, BT, Orange, Vodafone, NTT, Blanche Geo, you name them, you pick your favorite, I won't say customer, they're not your customer, they are your service provider. Pick your favorite service provider. They are seeing that they need to spend more money on the infrastructure of the network, but are they getting extra money, or are they getting paid more because they need to add all this capacity? Absolutely not. So they need to find more cost-effective ways to run the network more efficiently. So they are forced to innovate. Like I said, the second bullet is talking about the traffic is increasing on the network, and subscribers like you and I, we are not willing to pay more extra money. Or if they're going to bill us one particular amount X, suddenly they say it's going to be Y, we will probably stop our service with them and go find another service provider. So they are afraid of losing customers too. Another point to note here is that traditional phone lines are disappearing. These days, people make calls on WhatsApp, they make video calls, they make voice calls, we all do it. We watch videos on Netflix, Amazon Prime, right? Do we buy specific bandwidth or internet access for it? No. We just pay one flat fee to the service provider. You might have a data plan on your cell phone, or if it's a PC or a server, you might buy internet access through ISDN or ATM frame relay, doesn't matter. You basically buy internet. That's it. You buy something, and then on top of that, you have your voice traffic, be it WhatsApp video, audio, Vonage video, Netflix. You put all of this traffic, you play video games, right? You can watch TikTok videos, doesn't matter. All of this are riding as applications on top of the network. But the network service providers don't get any money. And because people are making more and more WhatsApp calls, the traditional landlines that BSNL used to offer, that's getting cut. So some of these providers don't make enough money as they used to make money. In fact, their revenue is not even remaining flat, it is declining. Like just in my case, I have cut all of my landline telephone because I'm using voice over IP. So as long as I can have internet access, I'm able to call any part of the world. So I don't need to buy that particular dedicated telephone line. So customers are losing money right there as well. And all of these reasons is forcing customers to make sure that they buy cheaper hardware or they find innovation so that it doesn't cost them a lot. And maintaining this network is extremely hard, complex, and customers like us do not want to see the network outage. We don't want to ever be in a situation where we don't have internet access. So what happens is, to maintain this network, the operational complexity goes up, and every time it is complex to add bandwidth, troubleshoot a failure in the network, you need more people. You need more power to power these routers. You need cooling because these routers are all making all kinds of heat generation, and it costs real estate to house all of these routers. So the operational expense is going up again, and customers or service providers need to keep it down. So all of these reasons are forcing them to innovate. There is this concept of traffic engineering. We have time. I want to spend at least 2 minutes on this. If you forget the slide for a second, right? Like I keep giving this example of traffic between, say, Bombay and Chennai. Chennai is in the East Coast, Bombay is in the West Coast. If somebody is getting on a truck or a car and they're trying to drive, they're going to probably use a highway which has too many open lanes, too many free lanes. There may be a national highway that has 4 lanes. If there are more and more cars that take the highway, there could be a traffic jam. Sometimes when you have a traffic jam and there is traffic congestion, you don't have to put more and more cars on that same highway. You may perhaps need to consider putting it on a back road that may only have 1 or 2 lanes. It's not the best of road, but when the highway, national highway, is congested, it makes sense to put the traffic on a road which is probably like not even well maintained. It has potholes. It may go through some towns and villages and perhaps residential area. So you cannot drive fast, but it is better than being congested here in the national highway. And that happens in the network as well. So if you see these routers R1 and R2 trying to send traffic to R3, R2 and R1 are preferring this path here because there is a lot more bandwidth here. Let's say we have hundreds of terabytes of bandwidth here. So when you have 100 terabits of bandwidth here, and let us say there's only 10 terabits here, you want to send traffic here. But what happens is when there are more and more traffic coming here and it exceeds 100 terabits, you need to naturally switch some of this traffic to this other path here. So shortest path first would put your traffic here. OSPF and ISIs show you the best path to go here. But guess what's happening? Maybe, like I said, there's this congestion happening. And in that particular scenario, you're changing your SPF. Instead of finding the best path, which we call shortest path first, you want to have a constrained shortest path. And that's what traffic engineering does. MPLS stands for multi-protocol label switching. And there is a whole lot of information pertaining to MPLS. We won't have a whole lot of time to cover MPLS here. MPLS brings several use cases, and traffic engineering is just one of the use cases. And I'm intimately familiar with this because I work on these routing protocols. I've written some papers. You can search that, or I'm happy to share it. Our books like Tannenbaum doesn't talk about it because these protocols were invented many, many years later after the Tannenbaum book was written. So there's this protocol called BFD, or bidirectional forwarding detection, BFD. Basically what happens is this router sends a packet hello message every 15 milliseconds or so. And if it misses 3 hello messages back, it will declare this link as failed. And all the traffic coming here instead of getting black hole here or dropped here, would get routed through this link. Of course, the bandwidth here is not a lot. Yes. So if you only have like 20 terabits and you're trying to send 100 terabits worth of data here, there is going to be congestion. Some traffic will be lost, but not all traffic. In which case, the service provider here needs to add more bandwidth here or find another path or work with another customer and buy another partner of theirs and buy maybe from Vodafone and buy link to go here, or troubleshoot and figure out what went wrong here. Maybe roll a truck that will go and investigate what is wrong here, or some of this could be software bugs, in which case instead of rolling a truck or a technician, they could fix the problem. Traffic engineering brings a lot of features here. These are all like almost like alphabet soup here, buzzwords. I'm just listing this here because if one of you, a few of you, are interested in working on these projects or protocols, I just want you to walk away with notions and concepts called policy-based tunnel selection. So how do we make sure that if there is only 10 or 20 terabits available here and there are 100 terabits of traffic coming here, which customer do we prioritize? Obviously, you need to prioritize a business customer like a ICICI Bank trying to transfer money or Bombay Stock Exchange trying to buy stock. They obviously need that bandwidth. They are willing to pay extra. A doctor at Apollo hospitals may be working on a patient remotely, and if they're doing a surgery, that is a mission critical application. That needs to take precedence over me trying to watch a T20 game perhaps. That's not important. Watching a T20, even though we may think it's important, it's not as important as a surgery a doctor performs. So we need to make sure we prioritize certain traffic over other. That's why we have this protocol in place, or this notion in place called policy-based tunnel selection. We have auto bandwidth. A customer may buy a small amount of bandwidth to begin with, and then the bandwidth may grow. And when it grows, let's say this purple line here is Apollo Hospitals. It bought 10 terabits, and then it's slowly becoming 20 and 30 and 40 and above 50. And this previous yellow line that was using 50 terabits now needs to be preempted or sent to this not so great path. And what we do there is using this notion of auto bandwidth, we let the bandwidth of the network increase, and then we break this yellow and put them on this path here. So we preempt the yellow lane from the best path to the not so best path. So we preempt them, and that's possible with auto bandwidth. I talked about fast reroute when I talked about this link getting failed or going down here. When this link failure happens here, if you see my cursor move, we need to understand this link failed within 50 milliseconds and move the traffic through another path. Fast reroute, FRR. Now, let us say there is a customer here off of R1 talking to some customer off of R3 router. If this link failed and we route the traffic here, that particular phone call that was going here will now go here. And guess what? As end users, we won't even know, because 50 milliseconds is such a small amount of interval that you won't even know that the traffic had failed here, and that you're rerouting failure, because we're talking about 50 milliseconds. If a traffic loss is under 50 milliseconds, nobody would even realize that there has been a network churn and the path had to be changed here. I'm talking about a lot of high-level concepts here. This is probably the last slide. There are a few things service providers are doing, and I will try to wrap this in 4 minutes so we can set aside 10 minutes for question and answer. NFV is Network Functions Virtualization. SDN is Software-Defined Network. These are all real advanced concepts that schools and the curriculum in colleges wouldn't necessarily talk about it, but obviously there is enough of information material available online and in certain universities that are trying to do some high-level research on this, and there are several papers. I'm setting the stage up for you all. If you are looking for an area to do some theses on or to do some project on, maybe these are all cutting-edge technology areas where you may want to research further. I'm happy to talk to you all offline and get more information. But let's talk about this. Network functions virtualization. Virtualization where possible. Now, if I go back to this router here, this topology here, this Miami router, or let me take another example. Let's say this Detroit router. This is in the middle of the entire backbone here. It's taking lots of traffic coming from Seattle and every other places, and it's routing here. There'll be traffic from here, from the right-hand side going left, from top going down. There's all kinds of traffic happening in every direction here. Can I take this routing software and put it on a PC? No, my computer would crash. But if BGP or Border Gateway Protocol dictates that every router here has to know information about everything. This is a two-dimensional sheet. I have not been able to show a 3D view of this. There are customers hanging off of Boston. There are customers hanging off of Denver, off of Kansas City. So it's like a multi-dimensional paradigm, and you need to imagine there are customers everywhere. So whenever there is an external customer, external partner, or a peering point, you're learning routes. Denver is learning routes. Sacramento is learning routes. So all of these routes needs to be shared with each other. But because Denver is not talking to Boston, it cannot send the routes information directly. So if you have somebody in the middle here, right, like if you see my cursor move here, we call this route reflector. You can have a router here that will learn routes from everybody, and it will reflect it to everybody else. Now, is it carrying traffic? Hypothetically, if there is a router here, is it carrying traffic between Denver and Boston? No. It is only sharing the routing information. It shares with Denver what it learns from Boston, and shares with Boston what it learns from Denver. So if I have a function like that, maybe I can put it on an Intel chip and run it for cheap. So that's why we talk about virtualization. Example, route reflectors. Some of the provider edge nodes, if they are not carrying a lot of traffic, maybe you can put that on a server as well. So that's why virtual provider edges are also a good candidate for network functions virtualization. Now, there might be a need for a customer to separate the control plane and data plane. When I go back to a router like this, if this router here is carrying traffic, I call it data plane, because traffic and forwarding, it is happening at a plane called data plane. But what routes it learns from a route reflector that is sitting here doesn't necessarily need to be part of the same code base that is doing the forwarding. So any route learning new IP addresses, finding paths to reach certain IP address, to reach Australia or a different, let's say there is a new college coming up in Australia and they have a new IP address. So that particular IP address needs to be learned. That function of learning the routes that customers are looking forward to doing. Another notion is centralized controller computing best path. Now, for a router here to go to this particular node here, it can go A or it can go B. There are two possible paths here. But if I go back to a more complex network, for Kansas City to reach Los Angeles, it can go through Denver, Sacramento. It can go to Denver, San Jose, and come back to LA. Or it can go through Dallas, Austin. You get the idea. Like there are so many ways. The permutation and combination is way so many. So you need to compute the shortest path first, instead of doing that only from the perspective of Kansas City and Detroit-based chip, be it a HP server or a Dell server, doesn't matter. You can run all of this high-power computation here, and once you calculate the best path, you can use another protocol like PCE. I don't want to throw more terms at you all, but I'm forced to say that. There is a protocol called path computation element. So using that protocol, you can tell all the routers what path each one must take. So that's why you have this offline computational box. Now customers also want to separate hardware and software. So like my company, CISCO Systems, makes routers, really huge routers and some small routers too. So folks like British Telecom or NTT, Docomo, you just name it, when they come to us, they say, Cisco, or instead of Cisco, I could be Juniper, I could be Huawei from China, I could be like Alcatel-Lucent, doesn't matter. So they come to vendors like me and they say, I like your software, but I'm able to buy cheaper hardware from Taiwan. So can I just buy your software and put it on this Taiwan-based box? And can I still get the same routing functionality? Well, it's not going to be as cool because, first of all, I'm losing my money because I used to sell a router my hardware, my software, I used to package the price however I want. And when they say they're going to buy my software but not my hardware, that means I'm losing half of my revenue, right? But that's what customers, my customers, I'm calling them customers because that's what is registered in my head. But from your perspective, think of Reliance Geo going to Cisco, Verizon, sorry, Cisco, Juniper, ALU, Alcatel-Lucent. I'm just trying to give you all more names so that you know who I'm talking about. It could even be Tata Alexi, right? Like they're going to these places and they're saying, give me software that can run on cheaper boxes from Taiwan. And that's basically what it is, hardware and software disaggregation. And they want to lower their capital expenditure because if they don't do it, they're going to lose out in the marketplace. Already service providers are having a lot of debt and their share prices are not as high as some of the content providers. Like Netflix doesn't own a network, but their stock price is so high. Why? Because they're able to use the network already built. They are just at the application layer. They're leveraging the network that is built, and they don't have to pay for this infrastructure, but they are remaining more profitable. I see I only have 6 minutes. Just to sum up what I talked about, if you haven't caught everything that I said, I started by talking about what are some of the network architecture paradigms, what are routing protocols, why do we need routing protocols, what is traffic engineering, what are some of the ways customers and large service providers reduce the cost of the network using concepts of software-defined network. We talked about network functions virtualization. And I'd like to pause for questions. We have about 5 minutes, and I will stop sharing so you can see me better.
Yes. Good evening, sir.
Mm-hmm.
I have a question.
Yeah, ma'am.
How dimension of interconnection networks play a role?
The dimension, yeah. So I'm guessing this particular question is based on one of the topology diagram I showed, where because I could not represent a 3D, I showed how the network is from a topographical view, two-dimensional. But when you take a network such as that, the area of it goes up because a network is a network. It is talking to internal routing peers using ISIs or OSPF. And now it has to also talk BGP because any route it learns needs to be sent to all of its internal neighbors, either directly or through route reflector. And not only that, any routes it learns internally needs to be fed to the outside world as well. So if I'm a router sitting in Chennai and I'm learning about all the routes around Chennai, like Sri Perumbudur and all kinds of other smaller towns and smaller, I would call them IP addresses. I need to make sure that Bombay knows how to get to Sri Perumbudur. So I need to get the Sri Perumbudur route through ISIs or to OSPF, but I need to send it to Bombay and Delhi and all of that. So the scale of it increases as and when you have more routing adjacencies, be it internal or external. So that's a good question. Any other question?
Thank you, sir.
Yeah. We may be able to take at least one or two more questions. I wish this was another media where I could actually ask you all some questions as well to make sure that it's interactive, but also to check your understanding. I want to make sure that some of the concepts I shared are all received by you all the way I intend it to be. So for that, to check my, to cross-check the understanding, I would like to throw questions, but I cannot do it here. Maybe next time we do this, we got to plan better. Maybe have a questionnaire created or a poll created so that you can all answer. How can we, the question, I'll rephrase the question. If there is an attacker trying to compromise the network, how do we safeguard it? I wish I had the slide in front of me. So every router, when you look at the core of the network, it needs to make sure that it can stop things like denial of service attacks. So what happens is these days people either maliciously or inadvertently keep making requests. There is a protocol called ICMP, Internet Control Message Protocol. It's just to see if a server is up or a router is up, you send a ping message. You can literally get on a router and say ping com. When you say enter, there is an ICMP control message that goes to Google, and the Google server will send a response back saying, yes, I'm up. So you come back. the hello message comes back, and it takes 3 milliseconds to go to google.com. Next, I say ping www.cisco.com. That server might be closer. I get a response back in 2 seconds. So what end users sometimes end up doing is they keep pinging constantly, like million pings back to back, just to make the server be busy handling requests from these ping messages, and the router cannot route. So if you intentionally want to bring a particular server down or a router down or ICICI bank down, end users, for whatever reason, may want to attack that particular server, and we need to be able to prevent that. And this particular attack is called denial of service attack, because we are denying the service of what the router needs to be doing. So we have mechanisms in place. That will be a longer, deeper discussion to exactly talk about how a DDoS is being mitigated. But be rest assured that there are filters, mechanisms, checks in place at every part of the network, and more so at the edge of the network. Because when you think of a core of a network, it's all like managed by one provider. But when you look at the access technology, that's where end users that are hanging off of these access network, if they are trying to do something malicious, they may want to steal certain information, spoof certain data. That can happen more on the edges of the network, but even there we have enough filters, checks and balances in place. Great question. I think that brings us to the end of the 1 hour session.
Hi, good evening, all. On behalf of CTTE College for Women, I take this opportunity to propose a vote of thanks to all who have contributed to this webinar on recent trends in networking, conducted by the Department of Computer Science. We are very thankful to our Honorable Chairman and Correspondent for their support. At the outset, I thank our resource person, Mr. Jay Karthik, for accepting our request. We are really enlightened with your presentation and knowledge, sir. I would like to thank our principal in charge, Dr. R. Meenakshi, who has been a pillar of support in all our endeavors. A special thanks to our head of the department, Mrs. Mary Catherine, my colleagues, Shuganti and Dr. Lalita and Hemavati for the support and coordination. Our heartfelt thanks to our active participants from various colleges and students belongs to CTT College. Hope we'll be having more session in the upcoming days. Thank you once again. Stay home, stay safe, stay positive and gain knowledge. Goodbye.
Thanks, ma'am. It was a pleasure. I'll end this meeting. Appreciate it, folks.